Hello learners, I welcome you all in my lecture series on Physics of Nano Materials for Physics 2. Myself Dr. Sucharita Bhattacharya, Associate Professor of Physics from Guru Nanak Institute of Technology, Kolkata, is delivering my lecture session for third semester BTech course, and the streams under considerations are Computer Science and Engineering and Information Technology. Today I am going to deliver the lecture 1 of this lecture series on Physics of Nanomaterials. Now let us take a look at the syllabus. This Physics of Nanomaterials come under the module 5 of Physics 2 with code PH301. You students know that there are total contact hours of 3 lectures per week and the credit is 3 and total number of lectures to be delivered is 36. Now, in Physics of Nanomaterials, 4 lectures are there. So, what is included in the corresponding syllabus? Let us take a look. Reduction of dimensionality, properties of nanomaterials, then quantum wells, 2-dimensional, quantum wares, 1-dimensional, quantum dots, 0-dimensional. Then we will go for applications of nanomaterials in the areas of electronic, environment and medical applications, as well as to very special area in the form of CNT, that is carbon nanotube, and the graphene. Now what about the corresponding course outcome? After completion of this course, you students will be able to define materials at the low dimensions. You can explain their various properties. You can analyze role of quantum confinement in inducing novel feature of a nanomaterial. And finally, you can apply this concept in various areas of modern technology. Now, the books you may consult are as follows. Nanotechnology by Rakesh Rathi, which is from S. Chand Publications. Then you can look at Nanoscience by H.E. Schaeffer, that is Springer Publication. And another very good book is there, that is Nanotechnology by Rogers, Penather and Adams, which is published by CRC Press, that is Taylor Francis Group. Now, for detailed syllabus and the books, the students, you may consult the website www.gnit.ac.in syllabus. Okay. So, let us start our today's session. Now, already I mentioned that today we are starting the Physics of Nanomaterials, where total 4 lectures are there. So today we are starting our first lesson, where we are going to start with introduction, then classification of scales, miniaturization, then scaling law, surface to volume ratio, and then we will start discussion on reduction in dimensionality. Okay. Naturally, the questions to be addressed in today's session is that the Feynman, the father of nanotechnology, why he is called the father of nanotechnology. Okay. Next one, size scale classification. We will go for that. What about size scale classification? Then why miniaturization is required? Then what is scaling law? Obviously, because size scale classification already mentioned, then miniaturization is there. Then what is scaling law? Next, surface to volume ratio. I already mentioned that today we will cover surface to volume ratio. What is its importance insofar as nanoscience and technology is concerned? Next, the reduction in dimensionality, the possible output. Today actually we will give the outline. In the next class we will go for the very detail in reduction in dimensionality. Okay. Now let us introduce with Feynman's vision. Richard Feynman is considered to be the father of nanotechnology. Now, why he is considered as father of nanotechnology? To get an idea, to give an idea rather to you, let me share a very short but interesting story where Richard Feynman was the main character. Okay. It was way back in 1959, a cold December 29 itself, in annual banquet of American Physical Society, Feynman was invited to serve as the featured speaker. There are around 300 renowned physicists gathered there, and Uhlenbeck invited Feynman, and he accepted the invitation to serve as featured speaker. Then, on the very evening, he started talking on a topic entitled "There's Plenty of Room at the Bottom." Just look at the title. There's plenty of room at the bottom. So all the physicists, they were astonished that what about this? There's plenty of room at the bottom, and what Feynman will talk about. Now Feynman started talking about a field for which no name was decided then. He started talking about the possibilities of small sizes. How much small? The size of atoms. He started talking about the possibilities of small sizes. How small? The size of atom. Actually, he is Einstein's picture. This is the, he started talking about nanotechnology. So he started talking about the nanotechnology in the form of the possibilities of the small object. How small? It is in the atomic scale. Nowadays, it is the nanotechnology, the name with which you are familiar. Then he started posing challenges there in the form of to write the Encyclopedia Britannica, the entire Encyclopedia Britannica of 24 volume on a pinhead, the possibilities. Next, to make an electron microscope that could see the individual atom. Next, to build a microscopic computer, and ultimately to arrange atoms the way people want. So when he started talking about the possibilities of size of the atoms, then he started posing the challenges that if it is possible, then you can write the entire Encyclopedia Britannica of 24 volumes on a pinhead. You can you can make an electron microscope that could see the individual atom, or you can build a microscopic computer, or even you can arrange atoms the way you wish to do it. Now, as references, he exampled few natural phenomenon or other the components in our body parts in the form of DNA and the human brain, where we all know that miniaturization was wildly successful. So when people were surprised that is it possible to look at the challenges, then he started taking the references of the natural examples of DNA and the human brain, and where the miniaturization is successful from the very beginning, so all understood. Then, to their surprise, he offered a pair of $1,000 prizes for which purposes? To create an operating electrical motor not larger than 1 by 64-inch cube. And second one, to take the information from a book's page to put it on an area of 1 by 25,000 times smaller in linear scale so that it can be read by an electron microscope. So he offered two prizes, each worth $1,000. For which purposes? That for a person for the first time, who can create an operating electrical motor not larger than 1 by 64-inch cube. And what about the second one? To take the information from a book's page to put it on an area 1 by 25,000 times smaller in linear scale so that it can be read by electron microscope. To his dismay, he found that within 4 months of his speech, William McLellan did the first one using tweezers and a microscope and won the first prize. Then the second prize was won by Tom Neumann, a graduate student of Stanford University, who won the second prize using a specialized electron beam writing program to transcribe the full first page of A Tale of Two Cities, the very famous one by Charles Dickens. That means Feynman's vision realized. Rather, Feynman's vision started realizing. It is the beginning of beginning. That's why Feynman is considered to be the father of nanotechnology. So I hope you students, you are engineering students, you are understanding what a physicist did so far as nanotechnology is concerned, so far as idea is concerned. He started with the idea, and all the people throughout the world then accepted the idea and the corresponding challenges to make it realizable. Okay, so this is the introduction and this is the Feynman's vision. Now, before going to the detailing, let us take a look at the scaling in macro, micro, and the nano range. Now, what about the range of the macro scale? It is starting from 10 to the power minus 3 meter and it goes up to 10 to the power minus 1 meter. So far as scaling is concerned, definitely all macro material around us, they are multiples of these scalings. This is the scale 10 to the power minus 3 meter to 10 to the power minus 1 meter. And the examples come under this category is our hand, whose dimension is of the order of 10 centimeter. The insect you can think, whose length is of the order of 2 millimeters, say. Now, what about the micro scale? It is from 10 to the power minus 6 meter to 10 to the power minus 4 meter. So micro scale category, we are getting human hair. The dimension is 10 to 50 micrometer. RBC or red blood corpuscles are the cells which have the diameter of 2 to 5 micrometer. Then come under the nanoscale. What about the nanoscale? 10 to the power minus 9 meter to 10 to the power minus 7 meter. Basically, 10 to the power minus 9 meter is termed as 1 nanometer. So, it is 1 nanometer to 100 nanometer because 10 to the power minus 7 meter, that is the range of the scale. Now, what about the corresponding examples? The visible light. We know it comes under the range of 4,000 to 8,000 angstrom. That means it is falling under this category of 10 to the power minus 7 meter. Next come to the nanoparticle whose diameters are in the range of 1 to 1,000 nanometers. Okay. Now, cesium, the single largest known atom whose diameter is 0.53 nanometers. That means each individual atoms also come under this nanoscale range. So I think the things are clear to you so far as the scaling is concerned. Around us, we used to get everything in the macro scale. Then comes the micro scale, and now it is the nanoscale, which is our scale of interest. Okay. Now let us come to the physics of nanomaterials, the miniaturization. Now what about nano? Nano means dwarf in Greek literature. So nanomaterials or nanoparticles are the set of particles or the substances where at least one of the dimensions out of possible three, at least one of the dimensions must be in the range of 1 to 100 nanometer. That means less than 100 nanometer, already we got it. That 1 to 100 nanometer must be the dimension, at least one of the dimensions of a substance. If we get, then we can say that these substance come under the category of the nano range, where I already mentioned 1 nanometer means 10 to the power minus 9 meter. Definitely, this definition reflects the fact that quantum mechanical effects are important at this scale. Definitely, at this scale, the quantum mechanical effects are important. Now, why nano or so small range? Now, it has been found that with miniaturization comes multifunctionality, and functional density improves exponentially with smaller parts. Very, very important statement. With miniaturization comes multifunctionality and functional density. What about functional density? Number of functions performed by a product per unit volume. It is improves exponentially with smaller parts. What do we mean by that? Let us take a look. A 100-fold improvement on the linear size scale transfers into 100 cube by volume. Obviously, 100-fold means 10 squared. Improvement on linear size scale transfers into 100 cube. That means 10 to the power 6 by volume. What is the meaning of it? That 10 to the power 6 times more circuitry you can stuff into the same volume. That means it is told that with miniaturization comes multifunctionality. Now, when you are doing the 100-fold improvement in linear size scale, then you are getting 10 to the power 6 times more circuitry to be stuffed into the same volume. Naturally, miniaturization gives you the multifunctionality. Actually, the engineering benefits of smaller systems can justify the cost, obviously, inherent in designing and building them, because shrinking something or taking something very small means you are requiring less material. Naturally, there will be less cost and it will occupy less space naturally. Also, smaller systems perform faster as they have less mass and less inertia. So from all practical point of view, these are the engineering benefits of the smaller systems which are used in different technologies. That less cost, less material means less cost, less space, and faster in so far as the work is concerned. So these considerations, depending upon these considerations, different engineering decisions are taken and are of utmost importance in many application areas, particularly to mention the satellite and the spacecraft systems. Here you require definitely less material, less cost, and faster movement. Okay. Smaller devices are imperative in case of medical field, enabling the surgical and the imaging techniques unprecedented way. Definitely in case of this medical imaging process, the nanotechnology, it is an invention, just like the case of satellite and the spacecraft system. Different other huge number of areas we have to mention in our due course. Okay. Now let us come to the scaling laws. The effective estimation of change of characteristics of something or some product as its dimension changes are generalized as scaling laws. So, effective estimation of change of characteristics. We are starting in that direction. We are going in that direction, that how to estimate the change of characteristics of something as its size or the dimension changes, and these are generalized as scaling laws. Now, let us first explore the implication of these scaling laws, starting with larger objects. That is the macroscopic body, sizes between, say, an elephant and an insect before considering the atomic scale. So, let us start with scaling laws in case of larger objects. For example, the case of an elephant and an insect before considering the atomic scale. Now, each of the three dimensions in a volume, let us generalize it in terms of a characteristic dimension, say capital D. Then surface to volume ratio of any solid can be scaled very easily as surface by volume proportional to d square by dq, that is proportional to 1 by d. Now, this relationship is a way to characterize things and to predict, for example, the difference between, say, energy and power the elephant and the insect need. How to relate the surface to volume with this energy and power, more specifically, their strength to weight ratio. Let us estimate it as follows. So, using the scaling law and the characteristic dimension, now let us estimate the strength to weight ratio of the elephant and the insect. Now, the strength of a muscle is roughly proportional to the cross-sectional area of the muscle. So, strength is proportional to d squared. On the other hand, a muscle's weight is proportional to g cube. Why? Because weight means we know that m into g. Now, g is the acceleration due to gravity. It is remaining constant. That means muscle's weight proportional to m. Now, what about m? M means density into volume. Now, density of a matter, unless otherwise specified, is considered to be constant. That means muscle's weight proportional to volume, that is d cube. So, what about strength to weight ratio? Here we are getting 1 by d. Previously we got surface to volume in general 1 by d. Now here we are getting strength to weight ratio in an approximation as 1 by d. Now let us come to the implication of this surface to volume ratio relationship with strength to weight ratio. For that purpose, the elephant we are considering, whose characteristic dimension is of the order of 1 meter, whereas the characteristic dimension of an insect is of the order of, say, 1 millimeter. That means surface to volume ratio for the elephant is 1 meter inverse, whereas that for insect it is of the order of 1000 meter inverse, because its characteristic dimension is 1 millimeter and surface to volume is coming out as 1 by d. So, for the case of elephant, mind it, the surface to volume ratio is coming to 1 meter inverse, whereas that for insect it is coming out to be 1000 meter inverse. And already we got their strength to weight ratio coming out of the same order as surface to volume ratio. That means elephant does not have sufficient strength to overcome its weight to jump. It is 1 meter inverse. So, the elephant does not have sufficient strength to overcome its weight to jump, whereas the insect can jump hundreds of times the size of its body. Just take a look. It is very funny. It appears like that. Definitely, it is a simplified explanation, but it gives you definitely the idea that a bigger size animal, that does not mean that it is very strong enough in all aspects compared to a small insect, so far as this idea of surface to volume ratio and size effect in the small scale range is concerned. I hope you are understanding, isn't that? Now, let us come to the practical case of scaling in mechanics. This is a funny one, but I tried to give you some basic idea in the form of a fun. Now, let us come to the scaling in mechanics. Now, address the scaling laws in mechanics where characteristic dimension, as we mentioned earlier, is again D. But we assume all material properties like say density, modulus, strength of the material are constant. So density, modulus and strength are considered to be constant, and all the linear dimensions vary proportionally to D as we already considered. Now come to the case of mass. I mentioned it that it is volume into density. Now density is constant considered to be, so mass is proportional to volume, that is dq. Now let us take as an example the case of gravitational force, the most common one, which expresses the force of gravity, that is the weight on an object. Now just take a look. F equal to mg, the force of gravity proportional to dq, because g, the acceleration due to gravity, it is a constant 9.8 meter per second square. Now consider as an example a dust particle and a rock. Now dust particle measuring 10 micrometer across is 10,000 times smaller than a rock 10 centimeter across. Okay. So the force of gravity is 10,000 cube or 1 trillion times less for the dust. So it remains airborne, but the rock is not. Are you getting the things? I am repeating it. A dust particle, say the dimension is 10 micrometer. It is 10,000 times smaller than a rock. Say dimension is 10 centimeter. So what about the force of gravity? It is d cube. So 10,000 cube or 1 trillion times less for the case of dust, more for the case of definitely the rock. So dust particles remain airborne where rock can't. So I think now you are understanding why I tried to say the previous one, though funny, but it gives you something so far as surface to volume ratio and size effect is concerned. Isn't that interesting? Now let us come to the case of reduction of dimensionality. But these physical characteristics of a substance, that is surface to volume ratio, consisting of large number of constituent particles, can affect the way they behave with one another and with particles of other substances. Now come to the case of practical situations. Normally around us we have the particles mostly, we have the objects mostly in the macroscopic range. So large number of atoms and large number of particles are there. Now we will consider the surface to volume ratio factor consisting of large number of constituent particles, how they can affect the way they behave with one another with particles of and with particles of other substance. In the same matter, large number of particles are there. So how they behave with one another, so far as surface to volume ratio is concerned, and if in place of a single substance, if you consider the neighboring other substances, definitely how they can interact with each other. In chemical and the physical processes, you all know only the surface of an object is exposed to the reaction and participate in the processes. We all know that only surface atoms are very proactive so far as reactivities are concerned to other neighbors. While a bulk solid material with large number of atoms may typically have less than say 1 to 2% of its atom at the surface, whereas a constituent particle with fewer atoms can be so small as to have say 85 or 80 to 90% of its atom on the surface. This is quite obvious. If you consider, say for example, a big structure of any material, say for example copper brick, if you consider, then millions of copper atoms are there. So definitely most of the atoms will be in the interior of the brick. Very less amount of atoms will be at the surface. Whereas if you consider a small copper strip, everything so far as properties of each individual atom is concerned, they are same because they are all copper atoms. But in case of the small copper strip, the most of the atoms are in the surface, not in the interior. So naturally, the reactivity and the exposure to the neighbors will be very much different. Here it is for an example, it is shown that if the large number of atoms you consider, then it may be 1% of the atom its surface. But if you consider very small one, maybe 85, 80 or 90% of the atoms on the surface. It is found as an example, a particle with 10 nanometer diameter has about 15% surface atoms, whereas 50 nanometer particle has about 6% of the surface atoms. So, for a given material, the crystal structure of a particle is not necessarily the same as the structure found in the bulk. Very much true it is. Because if it is the bulk, then you have large number of atoms which are in the interior. That means not at all reactive. But if you consider a crystalline structure, small one, the particle definitely, the particle alignment and so far as the structure is concerned, it may not be the same as that of the bulk one. So high surface to volume ratio of particles makes them inherently more reactive. This is another very important feature which I already mentioned here, that high surface to volume ratio of particles make them more reactive, obviously, like catalyst in chemical reactions. And this very basic property is exploited by the scientists and the engineers to quicken the commercial products. That high surface to volume ratio makes the particles more reactive. Naturally, you can use this property to quicken the commercial products with the reduction in dimensionality. So, in general, with reduction in size, what is happening then? The structure of atoms, atomic structure in the matter will change. At the same time, the reactivity of the atom with its nearest neighbors will vary. So what about the net effect? Obviously, novel electrical, chemical, magnetic and optical properties can be introduced. Very important one, because different properties you students all know, it depends on the reactivity of the atom and its structure in the material. So, with reduction in size, the novel electrical, chemical, magnetic and optical, actually these four are very much pronounced, that's why it is mentioned, but in different emerging areas, regularly the new properties are showing by the miniaturized material. Accordingly, newer applications are coming out in the true picture. So the resulting structure is then called the low dimensional structure. So reduction in size means you are talking about the low dimensional structure. What is the output? the novel properties insofar as electrical, chemical, magnetic, and optical areas are concerned. Obviously, this is natural because the confinement of particles, usually the electrons and the holes. In case of the conductor, it is the electrons. In case of semiconductors, it is the electrons and the holes. So, their confinement to such a low dimensional structure leads to a dramatic change in their behavior and to the manifestation of the size effect that usually fall under the category of quantum size effects. So, the change in their behavior, whose behavior? The confinement of constituent particles in the form of electrons and holes in the material like conductor, semiconductor to a low dimension obviously leads to the dramatic change in their behavior and to the manifestation of their size effect, which fall under the category of quantum size effect, and these are not at all shown by the large scale structure of the same composition. I already mentioned that if you consider the case of the copper brick and the copper strip, for example, definitely the properties we will see in our due course will be widely different. The same atom, the copper is there, for example, but properties are different because of the size effect. Accordingly, the nanotechnology with which the Feynman started his lecture. Okay. So nanotechnology manipulates basically matter precisely on an atomic, molecular, and supramolecular, that means many molecular system scale for fabrication of macroscopic products, refer to the broad range of research and applications whose common trait is size only. So nanotechnology definitely gave birth to a broad range of research and application where common trait is only the size effect. Okay. Now, the basic point remaining that how to use a broad, how to use the size effect to be manifested as a very special one so far as different characters or properties of the material is concerned from the individual solid, how to make a solid act more like an atom. That means how we can make a solid more like an atom. Solid means millions of atoms are there. So reactivity very small, structure reactivity is very small, structures are different. But if you consider the case of atom, each individual atom is more reactive with surroundings neighbor because it is exposed to all the neighbors. Naturally, you will get the different properties so far as their reactivities are concerned. So students, in terms of distribution of energy, solids have thick energy bands. Just take a look the way it is being developed. In terms of distribution of energy, solids have thick energy bands, whereas atoms have thin discrete energy states of the same material. So to make a solid behave electronically more like an atom, you have to make it about the same size as an atom by reducing the dimension. How do you understand that it is now behaving like an atom? You started with the solid, then you will see the thick energy band characteristic of the solid. Now you are reducing the dimension of the solid up to which you will reduce that when the energy band now changes to discrete energy level, you will be sure that the solid now has taken the structure of an atom by reducing the dimensionality, and it is the reality at present. Okay. So I hope you students understood in which way we are trying to move in our next session. So the reduction of dimensionality, the basic challenge is to make a solid act more like an atom. Then only you can encounter the different novel properties as we already mentioned. Okay. So thank you, my dear students. I hope you enjoyed the class. The totally new area and this area of the present era, obviously, and you students are engineering students, so it is your area, so we will explore that in next few classes. Till then, thank you.